Hey chemists, how you going? Today's video lesson we're going to have a chat about metal production. So this is the end of the using and controlling reactions topic for 12 chemistry. We've got the key ideas and intended student learnings here. I'm not going to talk about all of these, but we're going to be covering all of these in the video, and in particular focusing on the production of zinc from its ore as a specific example. So metal production, what is it and why we focused on it? So first of all, a lot of the metals that we find in nature will be combined with other elements to form rocks and minerals. Only the unreactive metals, so for example gold, will not be combined with any other elements because they're quite unreactive. But a lot of metals, as we know, are reactive, and they'll combine with other elements and other chemicals, so we need to not only dig them up, but we need to extract them as well. The more reactive a metal is, the less likely this metal would be found in its uncombined or elemental form. So if you get into some of the really reactive metals like sodium or potassium, you're pretty much never going to find them in their uncombined state. So we need to perform some chemical processes in order to extract them. So these metal compounds must be refined by industrial processes to produce the pure metal, which is what we'll be going through here. So I've just got an example of a metal reactivity series. The most reactive metals are up the top, and as you go down, they become less reactive down the bottom. I might start from the bottom here. So these metals, silver, gold, platinum, there'll be others as well, but this is just an example of some probably more common ones. These ones are found in an uncombined state. So if you go panning for gold, if you're lucky enough, you might be able to find some specks of gold by themselves, nothing more than having to dig it up, and then you're laughing. These ones here, so iron down to copper, we need to perform some kind of chemical reduction in order to obtain those metals. So oxidation reduction, so a redox reaction, where you want to reduce a solution containing these metals in order to get the pure metal itself. Here we need to have the electrolysis of a solution and or chemical reduction as well. Up the top, you need to have electrolysis of a molten electrolyte. So we can't have an aqueous solution of the metal ions. You need to have a molten ionic compound in order to obtain the pure metal. And we'll talk about the difference to that in a little bit, but essentially it's mostly to do with difficulty and cost. The more reactive metals are, the more difficult they are to actually extract. So we've got a 5-stage process in order to produce metal from ores. The first step in production is the extraction of the ore. So that involves mining. So essentially companies have to dig these big ores up. So that involves a relatively small or a big, depending on what the company is, mining operation. So open cut or underground would be different types of mining, and it involves a lot of machinery, a lot of money, and then you're digging up the product, which is your metal ore. Sorry, my head's in the way there. Concentration of mineral is essentially getting rid of all of the other parts of the ore and just focusing on the metal containing product. So that involves crushing the ore and separating the mineral from residue, and a couple of processes there, and one we're going to go through specifically is froth flotation. The product there is a concentrated mineral. The next step usually involves conversion of a mineral, so you need to perform a chemical reaction in order to convert it to something that's useful. So usually we do this by roasting, so burning the metal in oxygen to produce an oxide. So once you've done that, you've got your compound that's suitable for reduction. The reduction of the metal involves electrolysis to get the metal, and then once you have the metal, you can undergo a refining process, which is further electrolysis. Refining means making it more pure. So an example of production of metals is zinc, and this is the one that the textbook focuses on. So this is our specific example of production of a common metal. So the 4 major steps we're going to focus in, I've color-coded them so you can keep track as we go through. 1, 2, 3, and 4, concentration of the zinc mineral, conversion into zinc sulfate, purification into zinc solution, and electrolysis of zinc solution. And they match up these steps here. So we're just skipping the extraction of ore step because that's not really something we need to focus on. So the first step is the concentration of the mineral. So first of all, we crush the ore into small particles. Now, obviously, we don't crush it. We're not like it's not like a strawberry crack in year 10 where we're bashing it with our fists or anything like that. We're using big machinery, obviously, to crush these big ores. The point of crushing is to increase the surface area, okay, in order to increase the rate of the reaction. So that's an application of the rate of reaction content in this topic. Zinc sulfide is separated from the residue by the process of froth flotation. So basically we've got all of this ore and we use froth flotation in order to obtain this compound which contains the zinc, which is what we want. So zinc sulfide. What froth flotation is, it involves the powdered ore, so crushed very finely, being mixed with water in a large tank along with a frothing agent. And one of the most common frothing agents are these substances or these molecules called xanthates. Okay, so it's a kind of a class of molecule. So we'll have a look at these xanthates here. Oops. A xanthate is a two-part molecule. You've got an ion, which consists of a small hydrocarbon chain. So the hydrocarbon chain is hydrophobic, and this is connected to an ionic head. So that's the ion part, that's the charged part. That ion head is hydrophilic, and the heads are attracted to the ionic surface of the zinc sulfide particles. So here's our example of our xanthate ion. This is it here. So we've got the negatively charged ionic head, so that's polar. So that's something that is attracted to the water, and it's also attracted to the particles of zinc, okay? Because zinc sulfide is an ionic compound, so essentially the zinc sections of the zinc sulfide are positive because a zinc ion is positive, and that's going to attract ionically to that xanthate ion here. The hydrophobic end of the xanthate ion, we haven't done organic chemistry, but this zigzag represents a hydrocarbon chain. Every kind of point is a carbon, so carbon, 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 carbon. That's a hydrocarbon, okay? And we know that that's non-polar, okay? Now what this circular bit here is an air bubble, okay? So I don't know, when you make, I remember when I used to have my glass of milk, and when I was a kid, obviously I don't do this anymore because I don't drink milk anymore. Come on, you blow your bubbles in your milk, and it kind of froths up a little bit. It's a bit more complicated, but it's not really that much more complicated. So you've got your air bubbles of either nitrogen or oxygen, and that's blown through the whole mixture. So the bubbles are kind of rising to the top. Now those gases that the bubbles are made with, so nitrogen gas or oxygen gas, they're non-polar too. So the non-polar tail of the xanthate ion is attracted to that bubble, and that makes it kind of rise to the top. So the bubble rises to the top along with this section, and the polar head kind of attracts the zinc. So it's kind of like those toy things that grab a toy coming up to the top, and then they rise all the way to the top, and then you've got all your zinc particles at the top. Now once your zinc's at the top, because that's what you want, we skim it off, okay? Now there's a few photos that I've got, it looks kind of like this, so it's like metal froth, so it's just like a drink that has froth on the top, and these kind of machines skim the stuff off the top, which contains the metal, which is what we want, or the metal particles. This is a bigger scale, so this is a copper one, I think. So you've got somehow this big kind of wheel over here, the one pointing at the screen, goes around like that and skims the stuff off the top, and you can see it spilling over the side because that's the stuff that we want. The rest of it is not really needed, so that can be disposed of. So the next part is the conversion into zinc sulfate. So at the moment we've got zinc sulfide, that's what we skimmed off the top, ZNS. We roast it in oxygen in order to produce zinc oxide and sulfur dioxide. This is the chemical equation there, okay? That zinc oxide is then reacted with sulfuric acid in order to produce zinc sulfate in aqueous solution. So back at the first equation, we've got sulfur dioxide as a byproduct, so that escapes, and that can be added to water to produce sulfuric acid or something like that. So this can either be released into the atmosphere, which is not good, or it can be treated with other things. But we're not covering that too much here. What we are covering is the zinc oxide, so that there is dissolved in sulfuric acid, which is most likely obtained from this step here. So you get your sulfuric acid, and then that forms zinc sulfate and water, which is obviously not a harmful waste product at all. So we are left with zinc sulfate as opposed to zinc sulfide in the conversion step. The next step is the purification of zinc solution. So the zinc sulfate that we've just made here, it's not 100% zinc sulfate. There's a lot of impurities in there, okay? The impurities that we might have include other metal ions. So those might be things like silver ions, cadmium ions, copper ions, okay? Things that we don't want because we just want the zinc metal. Now, if they're left in solution, the reason why they're bad is because when the reduction step happens through electrolysis, these ions are going to be reduced in preference to the zinc ions. Now, why might that be? Have a think about it. I think that's enough time. The answer is these are ions of less active metals, so they are easier to reduce. Now, reducing will mean that electrons will be gained. Reduction is gain, so the metal ions are going to become the metal. Now, if that reduction is happening to this, then that's reducing our ability to reduce the zinc ions, which is what we actually want. So these things need to be gone. So the way that we do that is to add zinc powder to the solution. When you add zinc powder, so as opposed to zinc ions, actual metal zinc, there's going to be a metal displacement reaction. The zinc metal is more active than these metal ions in solution. You're going to get a single replacement reaction happening. So zinc plus the less active metal ions, we're going to get zinc ions, which will be helpful for the next step, and you're going to get this metal. Okay. Now those metals will obviously be solids. They're going to come out of solution, and then they can be removed. Okay. It's easier to remove the less active zinc ions into zinc metal. Okay. Impurities will also be present as more active metals, so you're going to have more active impurities as well. But they don't matter because zinc will be reduced in preference to these ones. Okay, so the fact that these more active impurities are there, like sodium and cadmium ions, that's fine. We don't mind about that. Okay. The last step, if you're not confused already, is the electrolysis of the zinc solution. So electrolysis, you've got your zinc sulfate solution running electric current through it in order to make the zinc ions go to the negative electrode, and then you're going to have the buildup of zinc there. So the half equations we're going to get, the thing that's going to be oxidized is going to be water. So water is going to lose electrons, and we're going to get oxygen, we're going to get hydrogen ions, okay, on this side, protons. So the oxidation of water and the reduction of water is something that we do want to memorize, I guess, because they do come into play a fair bit. The reduction is going to be what we want, so the zinc ions are going to form the zinc metal. And we've got a full redox equation down the bottom. Here's an example of, I've actually put the wrong diagram in there, just ignore that. I put a galvanic cell in there. This one is an example of the larger scale kind of electrolysis. So you've got these big vats and you've got this electrolysis going on. Okay, so that's our zinc. That was the example that we wanted to go through. Just a few footnotes for this process. If you're producing more active metals, so stuff that's more active than zinc, okay, they're produced from their ores by electrolysis of a molten ionic ore. Okay, so we're talking about stuff like sodium. We can't use aqueous solutions, so we use a solution of aqueous zinc ions. We can't do that with more active metals. because water is going to be reduced in preference to the metal ions. Okay, water is easier to be reduced, so it's going to happen. The more active a metal is, the harder it is to reduce. Okay, so we need to use a molten ionic compound. An example for that is aluminium, which is more active than zinc, is produced by the electrolysis of molten aluminium oxide. If it's a less active metal, then we don't have to do as much electrolysis. Okay, we can do a simpler process. We can reduce stuff less active than zinc by chemical reduction using carbon or carbon monoxide rather than the more expensive electrolysis. Here we've got iron oxide, so this is what iron would be combined with in its elemental state. Add some carbon and you're going to get carbon monoxide being formed and the metal. Same with here, carbon monoxide gas, and you're going to get carbon dioxide as a byproduct and the metal. Okay, so chemical reduction as opposed to reduction via electrolysis is an easier way to produce less active metals. The reason why this is significant is to do with energy costs. Okay, so this is the upside and the downside to these processes. The electrolysis of molten compounds, so for the really active metals, is expensive because there's high operating temperatures involved. We know that ionic compounds have high melting points, so you need to have machinery that's running at a high temperature, so it's expensive. Okay, so therefore, if we can perform electrolysis of aqueous solutions, we're going to do that because it's more cost effective. Chemical reduction is also better than electrolysis because it uses less energy and it's less expensive. Okay, so if we need to use electrolysis, we will, but if we don't have to, we use a different process. So that's why it's just important in industry to understand the chemistry of different materials to understand what process is the most cost effective, and this is an example of the decisions that chemists have to make. Guys, thanks very much for watching the video. I hope some of that, it cleared up some of that and it makes a bit of sense. I look forward to seeing what you make of it, and I'll catch you guys later.